Designing an electrical primary service requires careful consideration of various factors and adherence to relevant standards. Several design reference books can provide valuable guidance. Firstly, the National Electrical Safety Code, or NESC, covers the design, construction, and maintenance of overhead and underground transmission and distribution lines. This code is essential for ensuring the safety and reliability of electrical systems. Secondly, the Institute of Electrical and Electronics Engineers, or IEEE, 141.1993, which is the IEEE recommended practice for electric power distribution for industrial plants, offers guidance on the design and installation of electrical distribution systems specifically for industrial facilities. This document is a valuable resource for engineers working on industrial projects. Thirdly, IEEE 399.1997, IEEE recommended practice for industrial and commercial power systems analysis, provides methods for analyzing and designing electrical power distribution systems. This standard helps engineers understand the behavior of power systems and design them effectively. Fourthly, the American National Standards Institute, or ANSI, and the National Electrical Manufacturers Association, or NEMA, PB 2.2021, Electrical Power Systems and Equipment Voltage Ratings 60 Hz, specifies voltage ratings for electrical equipment and systems, ensuring compatibility and safety. This document is crucial for selecting appropriate equipment for a specific voltage level. Fifthly, IEEE 1584.2018, IEEE Guide for Performing Arc Flash Hazard Calculations, assist in calculating arc fault currents and arc flash protection boundaries. This guide is essential for protecting personnel from the dangers of arc flash incidents. Designing an electrical primary service involves a series of steps that ensure the system meets the required load demands and operates safely and reliably. The first step is load determination. This involves estimating the load demand in kilowatts and kilovolt amperes and determining the load characteristics such as peak and diversity factors. Accurate load determination is crucial for selecting appropriate equipment and ensuring the system can handle the expected demand. The second step is voltage selection. This involves determining the appropriate voltage for the primary service, considering factors like voltage regulation and voltage stability. Selecting the correct voltage level is essential for efficient power distribution and minimizing voltage drop. The third step is service entrance design. This includes selecting and designing service entrance equipment such as transformers and switchgear, and determining conductor sizes and materials. Proper service entrance design ensures a reliable connection to the utility grid. The fourth step is overhead distribution design. This involves laying out overhead distribution circuits, designing poles, crossarms, and conductors, and complying with NESC requirements. Overhead distribution systems must be designed to withstand environmental conditions and ensure public safety. The fifth step is underground distribution design. This involves designing underground distribution circuits and selecting and sizing cables, conduits, and transformers. Underground distribution systems offer aesthetic and reliability advantages but require careful consideration of soil conditions and cable protection. The sixth step is transformer selection. This involves determining transformer size, voltage ratio, and impedance, and considering efficiency, voltage regulation, and protection. Selecting the appropriate transformer is crucial for stepping down the voltage to a usable level and ensuring efficient power delivery. The seventh step is protection and coordination. This involves designing overcurrent, ground fault, and arc flash protection systems and coordinating protection devices to ensure proper operation. Effective protection and coordination are essential for preventing equipment damage and ensuring personnel safety. The eighth step is metering and billing. This involves determining metering requirements and installing and configuring metering equipment. Accurate metering is necessary for billing customers and monitoring energy consumption. The ninth step is inspection and testing. This involves inspecting and testing the completed electrical primary service system and verifying compliance with applicable codes and standards. Thorough inspection and testing ensure the system operates safely and meets all requirements. When selecting transformers, several factors must be considered. These include the transformer's kilovolt-ampere rating, which should be sufficient to meet the load demand. The voltage ratio, which determines the step-down voltage from the primary to the secondary side, should also be selected appropriately. Transformer impedance affects the fault current level and voltage regulation. Efficiency is important for minimizing energy losses and reducing operating costs. Voltage regulation ensures a stable output voltage under varying load conditions. Protection includes features like overcurrent protection and temperature monitoring to prevent damage to the transformer. Overcurrent protection is a critical aspect of electrical system design. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. This protects equipment and conductors from damage caused by overloads and short circuits. Ground fault protection is another essential safety feature. Ground fault protection devices detect and interrupt ground faults, which can occur when current flows through an unintended path to ground. This helps prevent electrical shocks and fires. Arc flash protection is designed to mitigate the hazards associated with arc flash events. Arc flash is a dangerous phenomenon that can occur when a short circuit creates a high-energy electrical arc. Arc flash protection systems use various techniques such as current-limiting devices and fast-acting circuit breakers to reduce the duration and intensity of arc flash events. Coordinating protection devices is crucial for ensuring proper operation of the electrical system. Coordination involves selecting and setting protection devices so that they operate in a specific sequence, minimizing the extent of any outage or damage. For example, if a fault occurs on a branch circuit, the branch circuit breaker should trip before the main circuit breaker, isolating the fault and preventing a larger outage. Metering requirements depend on the specific application and the utility's regulations. Metering equipment typically includes a meter to measure energy consumption, as well as current transformers and potential transformers to scale the current and voltage to levels that can be safely measured. Metering data is used for billing customers and monitoring energy consumption patterns. During inspection and testing, several tests should be performed to ensure the electrical primary service system is operating correctly. These tests may include insulation resistance tests, which measure the resistance of the insulation to ensure it is adequate to prevent leakage current. Continuity tests verify that all conductors are properly connected and there are no open circuits. Voltage and current measurements confirm that the system is operating at the correct voltage and current levels. Grounding tests verify that the grounding system is properly installed and provides a low impedance path for fault current. Protection system tests ensure that the overcurrent, ground fault, and arc flash protection systems are functioning correctly. In addition to the design reference books and menu items discussed, it is important to stay up to date on the latest codes, standards, and industry best practices. This can be achieved by attending industry conferences, participating in professional organizations, and subscribing to relevant publications. Proper design, installation, and maintenance of electrical primary service systems are essential for ensuring the safety, reliability, and efficiency of electrical power distribution. By following these guidelines and consulting with qualified professionals, engineers can create systems that meet the needs of their clients and protect the public. Understanding the specific requirements and conditions is paramount. For instance, environmental factors like temperature, humidity, and corrosive elements can significantly impact the performance and longevity of electrical equipment. Coastal regions, like Florida, often experience high humidity and salt spray, necessitating the use of corrosion-resistant materials and specialized protection techniques. Similarly, areas prone to extreme temperatures require equipment designed to operate within those temperature ranges, often involving dirting of components to prevent overheating. The type of load served by the primary service also dictates design choices. Industrial loads such as large motors and manufacturing equipment typically demand higher power levels and may introduce harmonic distortion into the electrical system. Commercial loads, such as office buildings and retail spaces, often have diverse load profiles with varying peak demands throughout the day. Residential loads, on the other hand, are generally more predictable but can still exhibit significant fluctuations depending on the time of day and seasonal factors. The utility company's requirements are a critical consideration. Utilities have specific standards and regulations regarding the connection of customer-owned equipment to their grid. These requirements often dictate the type of metering equipment, protection schemes, and communication protocols that must be used. Furthermore, utilities may impose limits on the amount of power that can be drawn from the grid at any given time, necessitating careful load management and demand response strategies. The National Electrical Code, or NEC, while not directly covering primary service design, provides essential guidance on many aspects of electrical installations. The NEC establishes minimum safety standards for electrical wiring, equipment, and systems, ensuring that they are installed and maintained in a manner that protects people and property from electrical hazards. While the NESC focuses on the utility side of the service, the NEC addresses the customer side, particularly the wiring and equipment downstream of the service point. Grounding is a fundamental aspect of electrical safety and is addressed extensively in the NEC. A properly designed grounding system provides a low impedance path for fault current, allowing overcurrent protection devices to quickly interrupt the circuit and prevent electrical shock hazards. The NEC specifies the types of grounding electrodes, conductor sizes, and bonding methods that must be used to ensure an effective grounding system. Overcurrent protection is another key area covered by the NEC. The code specifies the types of overcurrent protection devices that can be used in different applications, as well as the requirements for their installation and coordination. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage caused by overloads and short circuits. Wiring methods are also addressed in the NEC. The code specifies the types of wiring methods that can be used in different locations and applications, as well as the requirements for their installation and support. Wiring methods include conduit, cable, and open wiring, each with its own advantages and limitations. Equipment selection is another important consideration. The NEC provides requirements for the listing and labeling of electrical equipment, ensuring that it meets minimum safety standards. Equipment must be listed by a recognized testing laboratory, such as Underwriters Laboratories, or all, and must be labeled with its voltage, current, and other ratings. Arc flash hazard analysis is an increasingly important aspect of electrical safety. Arc flash is a dangerous phenomenon that can occur when a short circuit creates a high-energy electrical arc. The NEC requires that arc flash hazard analyses be performed to determine the potential hazards and to implement appropriate safety measures such as personal protective equipment, or PPE, and arc flash protection devices. Coordination studies are essential for ensuring that overcurrent protection devices operate in a coordinated manner. A coordination study involves analyzing the electrical system to determine the fault current levels at various points and then selecting and setting the overcurrent protection devices so that they trap in a specific sequence. This minimizes the extent of any outage or damage caused by a fault. Power quality is an important consideration in modern electrical systems. Power quality problems such as voltage sags, swells, and harmonics can cause equipment malfunctions and reduce system efficiency. Power quality monitoring equipment can be used to identify and diagnose power quality problems, and mitigation techniques such as filters and surge suppressors can be implemented to improve power quality. Renewable energy sources, such as solar and wind power, are becoming increasingly common. The NEC includes specific requirements for the installation of renewable energy systems, addressing issues such as grounding, overcurrent protection, and interconnection with the utility grid. Energy efficiency is another important consideration. The NEC includes requirements for energy-efficient lighting, motors, and other equipment. By using energy-efficient equipment, building owners can reduce their energy consumption and lower their operating costs. Commissioning is the process of verifying that an electrical system is installed and operating correctly. Commissioning involves a series of tests and inspections to ensure that the system meets the design requirements and that all components are functioning properly. Maintenance is essential for ensuring the long-term reliability and safety of an electrical system. Regular maintenance should include inspections, testing, and cleaning of electrical equipment. A well-maintained electrical system is less likely to experience failures and will provide a safer and more reliable source of power. In addition to the NEC, other codes and standards may also apply to electrical installations. These include local building codes, fire codes, and environmental regulations. It is important to be familiar with all applicable codes and standards to ensure that the electrical system is compliant and safe. The design and installation of electrical primary service systems require a thorough understanding of electrical engineering principles, as well as a familiarity with applicable codes and standards. Consulting with qualified electrical engineers and contractors is essential for ensuring that the system is designed and installed safely and reliably.